These are the frequently asked questions for pre-calculus for section 1, day 2, starting with number 21. It says a garden shop sells 12 by 12 square stepping stones for the same price as a 13-inch round stone. And if all of the stepping stones are the same thickness, which option gives the most rock for the money? Now, this is not going to be three-dimensional because it says the same thickness. That means this is just like the example we did in class where we were talking about the pizza, which one was the better buy. So what we need to do for the square stone is to just take 12 times 12, length times width, or in this case side squared, and that will get us 144 square inches of rock. But a 13-inch round stone has a radius of 6.5. So the area will be pi r squared, and we of course would use a calculator to figure out approximately that square inches there because we want to compare that to the 144. And this would be 132.732 square inches. I'm guessing that people missed the fact that a 13-inch round stone, that's giving the diameter there. So the most rock for the money, you're getting more rock with the square stone. So to answer this in a way that tells somebody exactly what's going on, we would say the square stone, because 144 square inches is greater than 132.732 square inches. And that way they know exactly what it was we were working on with number 21. So again, very similar to the pizza example that is in your notes, but my guess is that people use 13 for the radius instead of 6.5. And it didn't specify, so I suppose if you've never been a gardener, that would have been tough for you to figure out. Then the next one on your list, I give the smartboard a minute here. It gets cranky when I have the TI-84 emulator up there. So the next one on your list was number 23. And with number 23, it says a physics student obtains the following data. I must have hit it too many times. The physics student obtains the following data involving a ball rolling down an inclined plane, where t is the elapsed time in seconds and y is the distance traveled in inches. And what we were supposed to do with this was come up with a model. So if we want a model, that means we need to see it first. So I've already entered the data into this calculator. So under stats, number 1, I have 2 sets of data in here. This data I have in lists 3 and 4. So that data is going to match what we see in the physics experiment. So what I would want to do is I would take a look at the scatter plot. So second y equals, go into number 1, turn it on. But my data, because I didn't use the first list and the second list, I would have to let the calculator know, hey, go to list 3 and list 4. And that's just going to be second 3 and second 4. And then my window. I have to set that so that I can see this data. And t, the input, which is the x's, are from 0 to 5. So maybe I'll go from -1 to 6, just to make sure that I have all of those. And my y's are from 0 to 30, so maybe -1 to 50. Give it a little more space. Y and graph. And we do see a curve. And if you look back in your notes, we were told that this experiment will always produce parabolas. This will always be a squared in nature, which is a quadratic. So we need to do quadratic regression. We'll go into stats and arrow right once. And down at number 5 is quadratic regression. But again, I have my information in the 3rd and 4th list, so I have to tell it that. If this is all that you have in your calculator right now, then that probably showed up as list 1 and list 2, and that's exactly what you would use. I don't care about these pieces right here. I am going to store this, and I'm going to store that in those y variables. So variables, y variables number 1, because I'd like to see, you know, what does it look like? And then down to calculate and enter. And there it is. And I have A, B, and C, but I notice my diagnostics are not turned on. I don't see my R value or my R squared. So I'm going to hit second. Hang on. Catalog. Uh-oh. All right, hopefully. There we go. Because sometimes when I hit the buttons on the emulator, things don't go exactly as I would like them to go. So remember, we do second 0, and that's our catalog. And now I just have to keep going until I see diagnostics on. Yours are probably already on because we did that in class, unless you were absent, in which case this is exactly what you need to see, because we need to get the diagnostics on to see how good a fit we're talking about, because we want that correlation coefficient. That's what we're trying to find. Uh-oh, spinning wheel of death. There we go. And again, my computer is getting very old, so this takes quite a while to get this to. There we are. And I hit enter too many times. So it's going to continue to go for a while. And it's stuck. Hang on a second while I get that fixed. It would behave itself here, so I'm going to press enter at diagnostics on and enter again on the main screen to execute that. And now we'll go back into stats, calculate number 5, quadratic regression. And again, I'm going to get this to store it in y sub 1. You wouldn't have to do that part. This problem did not ask you to do that. And then calculate. And I see an R squared value of 1, which tells me this was a perfect fit, which, like I said, we know from the book telling us that this inclined plane experiment, the Galilean experiment, showed that this will always be a quadratic. So it is y equals 1.2 x squared, and that is the model with an R squared value of 1, which is a perfect fit, which is exactly what we wanted. So now, because this is going so slow, I think I'm going to go into stats and clear out those 2 lists in the hope that this will go a little bit faster. And remember, you can go up and highlight the name, hit clear, and then enter to get that list to clear out. All right, that was what they wanted in number 23. Number 24. The number of revenue passengers planed in the United States over the 14-year period from 1994 to 2007 is shown in table 1.7. That just means people traveling by air. So A is graph a scatter plot of the data, and let X be the number of years since 1994. So we're going to do that with the calculator, but what we're going to do is obviously make a little sketch on the homework so that I can see what you have. And I did already put this data in, so that was under stats and edit number 1, and that list is already in there. But what you have to do, because it was mentioned in the directions, is you have to use that first year as the 0 year. So you have to make sure that you're doing that, and you see that the years are going by ones. In fact, let me uncover this. We'll see that 1994, 96, 97, that's 95, 96, 97, it's going by 1. So we can just do 0, 1, 2, 3, 4, 5, 6, all the way down to the bottom, and then hop over to the second list and enter in the data that they gave us there. So a scatter plot of this data means that we have to get the data to fit with the numbers that we see. So we start thinking in advance about what we see, and our numbers were 0 to 14. And we have from 528.8 up to 769. So if we went 0 to 20 on our x's, and our y's, we could go 500 to 800. That should give us a pretty good look. So, window, 0 to 20, y1s, and then our y values hopped on me again, so 500 to 800. And second stat plots, go in and turn it on, and this time my data is in the first and second list. So second number 1, enter, second number 2, enter, and graph. And there's the data. So I have this scatter plot, and I can go ahead and try to reproduce that. And it doesn't have to be perfect. You don't need the exact same number of dots or anything like that. But this tells me that you got to the window you were supposed to be at when you graph that. And that's what we wanted to do. And then B says from 1994 to 2000, the data seemed to follow a linear model. Use that 1994 to 2000 points to find an equation of the line and superimpose that line on the scatter plot. Well, they're giving us specific years that they want us to use, which means, again, they want us to come up with this by hand. So, as we do that, we say, all right, they wanted 1994, that's right here. So, that's my 0 year at 528.8. And then they wanted the year 2000. Well, 1, 2, 3, 4, 5, 6 years later, or 2000 minus 1994 is 6 years. And for that one, we would use 666.2. So the first thing to do is find the slope. And the slope is the change in y, so 666.2 minus 528.8 over the change in the x's, 6 minus 0. So we'll get that as a decimal, 666.2 minus 528.8. And that's 137.4, and we'll divide that by 6. And we get 22.9. Now, always a good idea to use whatever model you have that would give you the zeros for one of your points. So, y minus y sub 1 equals m times the quantity x minus x sub 1 will be y minus 528.8 equals 22.9 times x minus 0. Which is great because that'll be y minus 528.8 equals 22.9x. And then we'll go ahead and move that negative 528.8 over by adding. So 22.9x plus 528.8. So there's our model. And what they want us to do is take that model and put it on the calculator. So back to the calculator we go. And we're going to go into y equals, clear out what I had for the other problem, and put in 22.9x plus 528.8 and hit graph. Not exactly the best line of best fit. You know, it really is above several of the points that we get there. But again, what you would do is on your paper and where that line was going, like so. And then C says, according to the linear model, in what year did the number of passengers seem destined to reach 900 million? Well, we go back and look, and we see that all of the data that was given to us was in millions, so we don't have to worry about any of the zeros messing anything up for us. We just have to use the equation and put 900 million in for y, and we will be able to work backwards and figure out how many years it took for that to happen. So we'll do 900 minus 528.8 divided by 22.9, and that gives us 16.2 years. So that means 16 years after we first started with this model. And this model first started in 1994. So we would take 1994 plus 16, and if the smartboard catches up with my writing, that would be good. Maybe I'll try scrolling up and see if it'll behave. It will not. I will write it up here. So we would say sometime in 2010. There it goes. So that would be our answer to part C. And D says, what happened here so that this model didn't work? I mean, the prediction here was that plane travel should definitely keep going. And of course, it was the terrorist attacks. So our last answer for D here would be the terrorist attacks. Something is off here. Hang on, let me see if I can get the smartboard to behave. All right, there we go. So for part D, the terrorist attacks on 9/11/01 caused a disruption in air travel. People were worried, so they didn't want to ride on the planes anymore. And it was pretty slow recovery to get people to want to be on the planes again. All right, now I am going to turn off the Graphing Calculator app. So give me a. So now in 37, the directions for this problem we're supposed to solve algebraically and confirm graphically. What we have to do to solve this algebraically is isolate the root. We need to move it to the other side. And to do that, you would add it to both sides of the equation. And now to get rid of the square root, we're going to square. Now when you do that, there is always the chance that you are going to have an extraneous solution. So if we do x plus 1 times x plus 1 and FOIL that out, we'll get x squared plus 2x plus 1. On the other side, the 2 squared is a 4, and of course the square root and squaring are inverses of each other. So this gives us x squared plus 2x plus 1 equals 4x plus 16. And now let's move everything over to one side, subtracting the 4x and subtracting the 16. And then our hope is that this is factorable. There is no common monomial factor, but if we have x minus 5 and x plus 3, that does what we need it to do. That gives us our zeros, which are 5 and -3. However, because we squared it, we need to check those answers and make sure that they are going to work. And of course, the way that they told us to check them was to go ahead and use the graphing calculator. So we go into y equals, and I want to see the original problem and put that in. And we had x plus 1 minus 2 times the square root of x plus 4. All right, let's try Zoom 6. Let's just graph that and see it. Because remember, we knew what the solutions were supposed to be. And we can see we're not getting a negative solution to this at all. So the -3 does not work, and the 5 does. So that's when the graphing calculator comes in handy, is just to check your solutions and make sure that they are going to work. So let's see, we have a couple more of these where we are solving them algebraically and verifying them graphically. Number 39, solve it graphically by converting it to an equivalent equation with 0 on the right-hand side and then find the x-intercepts. So they want us to do these totally relying on the graphing calculator. I guess I'm going to go ahead and move this one over by subtracting. So 2x minus 5 minus the square root of x plus 4 equals 0. And what we want to do is figure out where are the zeros. So let's see where those zeros are. Y equals, clear, and we have 2x minus 5 minus the square root of x plus 4. And we'll just try our good old Zoom standard first and see what we get. So there it is. So on number 39, we see that we have a 0. And we start thinking, well, should we only see 1? Well, you know, we had x to the first as our highest power, so yes, we should see only 1. And then second, calculate number 2, the zeros. I'm going to move Blinky into a little bit better position here. So this would be below is to the left. Oops. Always happens with this, it just gets carried away. So below it is left. Arrow to the right of the intersection, press enter, enter through guess.
Hakeem Porter to the
and we can see our 0, and we go to 3 decimal places, so 3.96. I believe that's an 8 back behind there. It's not the best looking image here, so 3.986. All right, next one up is 42. So again, I'm going to move everything over to one side and give this a try. So the square root of, and we have x plus 6. And we would be subtracting the 6 and adding the 2 square roots of 5 minus x. I'm used to my older calculator. There we go. And let's try Zoom 6. See if we can see what we need for number 42. And in number 42, it is the same thing. The highest power that we see in this one is x to the 1/2. So we should see one solution, and we do. Second, trace, calculate number 2. And this time, Blinky needs to be above it to be the left. And then Blinky needs to be below it to be to the right. And enter through guess. And there was our 0, 2.665. $44. Back to the calculator. And for 44, it would be x plus 1, but we would move everything, the cubic on the other side, over. So it would be minus x to the 3rd plus 2x plus 5. Again, I have an older calculator in class where I do not have to do all of this pushing it over. So give me a second here. There we go. There's x to the 3rd plus 2x.
Just a reminder.
And then we have a plus 5 to put in there. Let's try good old Zoom standard. Now this one has a cubic. So we look at that one and we realize, well, that's really only going to have one real 0 on it. You know, we see the other turning point and it did not reach the x-axis. So this one again, we want to get Blinky in position. Take care of those zeros for us. All right, so second, trace number 2, enter, below, enter, enter through guess, and we have approximately 2.355. 46. Let's punch it in and see what we get. And we have x squared there we go. And then minus the absolute value of x. That is under math, numbers, number 1, x. And I'll arrow out of there. And we'll try zoom 6 again. Negative 10 to 10 window. And with this one, what we would want to do is get a closer look, because with number 46, it's quite possible that we have more zeros than we can actually see. But I think, you know what, maybe I'll just try the table on this one and see what's happening at the table. So second table set, let's just start this at -1 and look at this by ones. Second graph, and we have 3 zeros, -1, 0, and 1. So for 46, -1, 0, and 1. Now, as I said before, a little bit suspicious of what's going on with this graph right at 0. So we could do zoom box and get Blinky in position here for the upper left-hand corner of the box. Press enter. Take your arrows down and to the right until we can see exactly what's going on the x-axis. Enter. And this becomes a little more obvious that we have a repeat 0 at 0. That's what's going on there. That's the reason that we only had 3 zeros. So that takes care of all the questions that you needed answered.